Hi, welcome to Log on Digital Analog to Digital Converters. Okay, as we discussed in the previous class, there's a block diagram of ADC, so which has the analog input voltage, and we are supposed to get its digital equivalent output. And of course, we have, as in case of DAC, we have a reference voltage. So we have three more pins over here. One is for start of the conversion, and we will going to get an end of conversion indication from the ADC that okay, it has converted that analog input to digital output, and we have a clock which is used for generating that digital equivalent of the analog signal. Of course, in the last class, we were also discussing about for the given input voltage. So how does that output will get? So this is what we are trying to discuss. So we actually took okay, V reference as equal to 1 volt. So and then we were trying to understand okay, what happens. So here also we have a LSB. So matlab, so least of course one LSB means uh, because the input voltages keep on changing. Input voltages keep on changing. Here also we specify one LSB is equal to VFSR by 2 power n, where n is number of bits. So there is number of, this is number of bits. Suppose if n is equal to 3, and if VFSR, VFSR or V reference voltage, okay, so where is equal to K into V reference. Suppose if K is equal to 1, then VFSR becomes V reference itself. Then I can say VFSR is equal to V reference itself. If this is the case, suppose if this is equal to 1 volt, if the value of n is equal to 3, will I get 1 by 2 power 3, which is equal to 1 by 8 as my value? What do you mean by 1 by 8 now? So what is 1 by 8? What is 1 by 8 in terms of voltage? Because this LSB is now in terms of, what is 1 by 8? Where is it? Can see. Hello. Is it
Yes,
125
sir, it
millivolt?
is 0.25. Yes, sir.
125 millivolt. The meaning of this is
Yes, sir.
if the output has to change, there should be a change of 125 millivolt at the input voltage. That's what is the meaning is.
Yes, sir.
If the output has to change, the input has to change by at least 125 millivolt. That's what is the indication if n is equal to 3. If n is equal to 3. The meaning of that over here is that assume that I have uh, the representation of transfer characteristics of an ADC.
Yes, sir.
Assume that this is the input voltage. So on x-axis, we'll always have the input, or the
The input
output.
voltage.
I'll have
Um, LSP.
on y-axis it is the
Bits.
output.
Yes.
Now, of course, you have the possible bits are if you consider n is
Zero.
equal to 3 and
Yes, sir. We have 8.
VFSR is equal to 1 volt. So I have it as 000, then
Yes, sir.
001, 010,
1,
011,
0,
1, sorry, 100.
0.
I'm just taking 2 unit as okay, 1 bit.
Um,
It is
yes,
now
sir.
101.
0,
Next, it is
110.
just
I think
this, 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 this. It should come out here. This is
yes, sir.
101, and this happens to
1, 1,
be
0.
110.
That one.
Next, it is
1, 1, 1.
111. Correct?
Yes, sir.
Now,
Yes, sir.
we have the input voltages starting from 0,
0 or
1
LSP.
by 8 volt,
1,
2 by 8
0.25.
volts, 3 by
Yes, sir.
8 volts,
By 8.
4 by
4 by
8
8.
volts, 5 by 8, 6 by 8,
6 by 8.
7 by 8.
7. Yes, sir.
This is the maximum voltage you can think of. Ideally speaking, what will
Yes, sir.
happen is, under ideal condition, So we are supposed to have, okay, till 1/16th of an voltage. Still one
Yes,
sixteenth of
sir.
an voltage. What is this 1/16th? Actually, 1/16th volt is nothing but half LSB.
Yes, sir.
This is half
Point
LSB.
one two five by two.
So this is half LSB. So from 0 to 1/6 of LSB, it is 000.
Zero.
Then
Yes, sir.
from
From
1/16 to
two
3 by
sixteen.
16, 3 by 16.
Yes, sir. Uh,
3 by 16, it is
yes, sir. Yes, sir.
011. And from this to this, it is,
Um, 010.
then it is this,
It is
then
zero
it
one
is
one
this.
100 101.
Okay, now you have,
Yes, sir. 110 and final voltage
because the input voltage is not going beyond this. Okay, if you want to
beyond this.
write beyond that, you can write it.
It will go up to me 0.875.
Uh, if you can notice, the transitions are happening for
Half LSP.
every
No, sir.
odd number
Of the
or
bit,
half
sir.
LSB.
Yes,
Is
sir.
this is one half
Half.
LSB? Is
Yes,
this
sir.
voltage is one half LSB? Is this
Yes, sir.
voltage is 3 by 1 by 16?
Yes, sir.
Is
Then
this
it will be
voltage
5 by 1 by
is
16.
5 by 5 into 1 by 16?
Yes, sir.
What I mean to say is the transitions
Correct.
from one bit to
Happens.
other bit will happen for every odd number of half LSB. Odd number of
Yes,
half
sir.
LSB.
Yes,
This
sir.
is how it will happen. Uh,
Yes, sir.
Corresponding to this, we're going to have an error signal. That's what we discussed in the last class. So in the last class, we have discussed that there is an error signal. So what do you mean by error
Yes,
signal
sir.
now? So assume that this is my 0. If the input voltage is 0, if the input voltage, okay, just take, if the input voltage is 0, are you representing it as 000?
Yes, sir.
Is there any
That's
error there?
correct state.
Is there any error?
No,
There is
sir.
no
Zero error.
error. So you say it as this is 0. There is no error. Now the
Yes,
input
sir.
voltage is 1 by 16. Are you still representing it as 000?
Yes, sir.
Are we actually underestimating the input voltage?
Yes, sir.
Input is actually half LSB. Your output is still stated as 000. You are
000. Yes, sir.
underestimating the input by minus half LSB. So
Half
that is
LSP.
maximum over here. So if I write this as my error, it is maximum over here. Is it minus half
Yes, sir.
LSB?
Yes, sir.
Okay. If the input is slightly more than 1 by 16, are you treating it as 001?
Yes, sir. We are reading.
So we are overestimating it by
We're
half LSB.
estimating it.
So then,
Yes, sir.
again, if the input voltage is 1 by 8, what is the output here?
It's
It is
exactly
001.
001.
There is no error. So that's why
Yes,
this
sir.
error will reduce and it continues like that.
Yes, sir.
Here, this is your transition. So I want each one of
Yes,
you
sir.
to write it and then show me. Let it take 5-10 minutes. I want all of you to write this quantization error graph. Even if it is on a plain sheet, write it. For every 1 by 8, 2 by 8, 3 by 8, 4 by 8, the error should be 0. The error, can you see here? The error is 0 here, the error is 0 here,
Yes,
the
sir.
error is 0 here. And for every transition, this quantization error should also change.
Yes, sir.
This is EQ, what is known as quantization error. The peak of quantization error is plus or minus half LS. Who is 14? 14, 14, who is 14? 14, can you share your screen? 14? Who is 14? Hello. Of course, at least you just put in the chat box, are you are done with this quantization error graph? May not be in a graph, so even if it is on a plain sheet, it is fine. Yes, respond in the chat box. Okay, are you all done or are you still doing it? This is a sawtooth waveform. This is a sawtooth waveform, the error signal. Okay, could able to see if you are seeing that if you are done with the values or done with the graph, make it fast. Can you see is this error signal is looking like a periodic signal?
Yes, sir. It is
This is like a periodic signal.
constantly happening.
If it is
Yes,
a
sir.
sine wave, if it is a sine periodic signal, if it is a sine periodic signal of amplitude, assume that it is V or maybe Vx. So what would have been its RMS value? Was it Vx by root 2, the RMS of the sine
Yes,
wave?
yes,
Similarly,
sir.
for this EQ, we will write the RMS. The RMS of EQ for a sawtooth signal will be equal to what is the peak of this? Peak by root 3 because of the shape of the waveform. If it is a
Yes, sir.
sinusoidal waveform, if it was a sinusoidal waveform, it would have been root 2. Since it's a
Yes, sir.
sawtooth, it is peak voltage divided by root 3. So what is the peak voltage? Peak voltage is actually half LSB. Am I correct?
Yes, sir.
This
Yes,
is
sir.
half LSB. Half LSB by root 3. Can I further write it as LSB
1/6.
divided
Yes,
by
sir.
2 root
2 root.
3?
Yes,
Can I
sir.
further write it as this is again
1/16 root 3.
EQRMS. EQRMS. Uh, what is actually VLSB? Sorry, LSB. Is it VFSR by 2 power n?
Yes, sir.
Can I write it as VFSR by 2 power n into root of 12 actually?
Yes, sir.
This 2 I'll take it inside, it will become 4. So this is my RMS voltage of the error signal. This is an error because this is whatever we are plotting is the error. This is the expected value you are getting it, and you are expecting something slightly more than 0, 0, 0, but it is still you are still representing it as 0, 0, 0 because I cannot represent anything other than 0, 0, 0 here. But still you are
Yes, sir.
underestimating the input. Why you are underestimating is because your number of bits are only 3. If the number
Yes,
of
sir.
bits are more than 3, then this okay you would have properly represented it as slightly higher value. Slightly higher value.
Resolution will be more. Yes, sir.
Resolution of the system or the ADC is less because you have lesser number of representation.
Yes, sir.
So we have an error signal given by so and so because we always talk about signal to noise ratio.
Yes,
Error is a magnitude. If you want to compare it, you have to always compare with a signal. Suppose if you have one line, you don't know how big or how small it is. if you want to know what is this line, so you have to have a comparison. You have to have a comparison. Now I can say this green one is lesser than the blue. Suppose if the blue is smaller, then I can say green is more than this. Meaning, suppose
sir.
if this is my noise, if this is my noise, then I can say noise is lesser than the signal. If the blue is signal. Now you can see this is signal, this is noise. Then I can say noise is okay more than the signal. So if I want to see whether this signal, sorry, this noise is too much or not, I need to always compare with the signal. I need to always compare with the
Yes,
signal.
sir.
So let us consider a signal which is a sinusoidal one having an amplitude VFS peak voltage as VFSR by 2. VFSR by 2 to maximize the signal to noise ratio. We are considering the V peak of the input voltage as VFSR by 2. This is the peak voltage of the signal. Then what is V signal RMS? Is it V peak by root 2?
VFSR. Yes, sir.
Is it VFSR
VFSR by 2.
by 2 by root 2? This is
Yes,
my
sir.
signal. What is my noise? V, okay, EQ by, of course, EQ RMS.
Yes,
Is it
sir.
actually equal to VFSR by 2 power n root 12?
Yes, sir.
Let me write it.
My
Let me put it
signal
here.
to V noise.
So we have signal to noise ratio.
Yes, sir.
We have now signal to noise ratio of an ADC as V of the signal by V of the noise. Noise here is
Yes,
quantization
sir.
noise. Quantization means when you are sampling, what is the error? When you are sampling, what is the error? So do we have it as VFSR by 2 root 2? This is VFSR
By
by
VFSR by 2
2
power n
power
root 12.
n root 12. Correct?
Yes, sir.
So does this VFSR and VFSL go off? So what do
Just
we
cancel
have?
this, sir.
Do we have
Ah,
signal to noise ratio as uh, 2
2 power
power
n.
n root 12 by root 8?
Yes, sir.
Is it now 2
Wait.
power n root of 12 by 8?
Yes, sir.
Now, usually this will be specified in terms of dBs. The noise ratios will be
Okay.
specified in terms of dBs. If I take it in dBs, then it is 20 log of
Pay log
2
of.
power n
So,
in the root of 12 by 8. Shall I now write it as 20 log of 2 power n plus 20 log of root of 12 by 8? What is this? This is what is, shall I write it as, what is 20 log of 2? Is it 20 log
20
of
log of 2 is
6.0?
6.02, sir.
Shall I write it as 6.02 n plus what is
Yes,
20
sir.
log of so and so? And the root of
Plus 20.
12 by 8, 20 log of that, 20 log of answer is 1.76. Correct?
Total 7.78. Yes, sir.
Correct.
Okay, sir. Yes, sir.
This is the
CM.
signal to noise ratio that is maximum possible if the input voltage is of VFSR by 2 as the magnitude. It's a sine wave.
Yes, sir. Yes,
If
sir.
the input is a sine wave, if the amplitude is VFSR by 2, then I'll end up with a signal to noise ratio, which is 6.02 n plus 1.76 dB. What does this mean here? Does suppose, okay, what is the ideal value of SNR? What do you suppose to have ideal value of SNR? Ideal value of signal to noise ratio is infinity. This is infinite, ideal value. Meaning, I need to have the signal to noise
V
ratio.
zero V. Yes, sir.
Come in.
The noise should be zero if it is ideal, right?
That's what. If it is zero, suppose this becomes zero, does this entire quantity becomes infinity?
Yes, sir, it will be.
Meaning signal to noise ratio should be as high as possible.
Yes,
So
sir.
looking at this, what is the possibility of making the signal to noise ratio as high as possible?
By increasing the number of bits we are
Only thing
using.
is that you have a n as a variable. If you have more and more n, then signal to noise ratio will want to improve. Correct? If your n increases by
Yes,
1 bit,
sir.
signal to noise ratio improves by 6 dB. Suppose if n of a ADC increases by 1 bit, then SNR will increase by 6.02 dBs. That's what is the meaning of this term, this particular expression. Okay? If the number of bits are more and
Yes,
more,
sir.
then it is better and better. Why it is better and better? Why this you want to
Because
improve?
the SNR value will increase.
Why that will improve is because your noise will reduce.
Yes, sir, typically.
Because one thing is that we have signal to noise ratio.
Yes, sir.
If this has to increase, one possibility is you increase the signal level or reduce the noise level. There are two ways of increasing the signal to noise ratio. I'm not
Yes,
doing
sir.
this. I'm not doing this. I don't want to increase the signal level and get a better signal to noise ratio. But I will
Yes,
do
sir.
this. This is my noise. This is my noise. How do you reduce the noise? Noise in this
By
case is
increasing the
nothing
number
but
of.
EQ.
Yes, sir.
Okay, what is EQ here? EQ is this. EQ is actually this. FSR by 2 power n root 12.
Yes, sir.
Suppose if you want to reduce the noise, only way is BFSR by 2 power n 12. So this is a better variable. Increase the value of n, then okay, noise will reduce. When I say n, it is the
Yes,
number
sir.
of bits that you are getting at the output. So instead of getting only 3 bit, you get 4 bit, you get 5 bit, you get 6 bit. Suppose if the number of
Yes,
bits
sir.
are more and more, then your EQ is less. EQ is lesser.
Yes,
Okay,
sir.
let us define some gain error and offset errors. We know that ideally, when does your first transition should happen? This is an ideal graph, correct?
Yes, sir. At first half LSP.
Okay, after first half LSB, your transition should happen, the first transition.
Yes, sir.
Suppose if the
Typically.
first transition happens at the zero or at 0 volt itself. Suppose assume that okay, you increase the voltage by very small amount from zero. If it goes here, then I'll say there is offset error.
Yes, sir. Initial
Sup-
error only. Yes, sir.
Suppose if the change happens at this point, if the change happens at this point, then I'll say there is an offset error by plus half LSB.
Okay. Yes, sir.
Suppose if I say if the transition is happening at this point, if the transition happens here, then I'll say there is an offset error of half LSB. If the transition happens here, if the transition
So direct.
happens here, I'll say it as
With
offset
zero.
error is minus half LSB.
So we take half LSP as initial point of reference.
Yeah, this is till half LSB output should not change. That is the ideal case.
Okay. Yes,
If it
yes, sir.
happens before that, then I'll say there is offset error. If it
And
happens
with
after
cancel.
half LSB, I'll say again it's offset error.
Yes,
Whether
sir.
it is happening before or after, I'll say that is plus LSB or okay, plus half LSB, whatever the LSB value, that will write it. If it is happening before, I'll say minus. If it is happening after, I'll say plus half LSB or plus LSB error, depending on where exactly it's happening. Suppose the transition happens here, then I'll say offset error is plus half LSB. If the first transition happens here, then I'll say the offset error is 1 LSB. The offset error is 1 LSB. Okay, that's what you mean by uh, offset error. Uh, then I'll have gain error. This is gain error. Uh, where is your first transition happening ideally? First transition happening ideally at
At the half LSP. Yes,
first
sir.
half LSB. Where is the last transition happening? Is it
At
happening here?
Yes, sir.
Is it
Before
happening
that.
here?
Yes, sir.
Is it actually happening? Is this is your FSV?
Yes, sir. Highest voltage.
Is this FSV actually 1 LSB less than FSR?
Yes, sir. Exactly.
Because FSR is VFSR is equal to 1 volt, correct? This 7 by 8, is it actually 1 LSB less than FSR?
Yes, sir.
Then where does your transition is happening? Is it happening half LSB less than FSV?
Yes, sir. Yes, sir. Hmm.
So
Um, one LSP.
you see the separation between, okay, now the last transition is happening actually 1.5 LSB less
LSB
than
before FS.
PFSR, correct?
Yes, sir.
Now, where does your first transition is happening?
At first LSB, half
At
LSB
first half
after the
LSB.
zero.
So,
Yes, sir.
between the first and the last transition, how much is the difference? Is it actually equal to VFSR minus 2 LSB?
Yes, sir.
There is half LSB gone here. There is 1.5
One and a half
LSB
LSB
gone from
gone.
FSR, from
Yes,
VFSR.
sir.
So, is the separation from first transition to last
Yes, sir.
transition, is it VFSR minus 2 LSB?
Exactly. Yes, sir.
Then we say there is no gain error. There is no gain error if the separation between the first transition and last transition is equal to 2FSR minus 2LS. Suppose
Yes,
if
sir.
the separation is other than this, if the separation is other than this, then I'll say there is a gain error.
Yes, sir.
If there is a gain error, then I need to adjust the gain such that the error is nullified.
Uh, yes, sir.
So first point is what is offset error? Offset error is said to be the error if the first transition happens other than half LSB. Right? Can you see it's happening exactly half LSB? So there is no offset error.
Yes, sir.
If it was happening here other than this point, if it happens anywhere else. So when I say anywhere else, we always take half LSB as the reference point. That is, it can happen here, it can happen here, it can happen here. Suppose if it happens here, how much is the offset error?
Uh, minus half,
From
plus half
from
LSP, sir.
from here, it's actually one LSB after that. I'm just pointing here.
Oh, sorry, sir. Yeah,
If
one
I'm
LSP.
pointing here,
Plus one LSP.
this
Yes,
is the
sir.
expected transition. If the transition happens here, then I'll say there is a offset
Half
error of
LSP there.
no here. If it is here, it is one LSB. If
Yes,
it is
sir.
here, from this is expected point, this is actually happening here. So if the first transition happens here, then I'll say there is a one offset error, one LSB offset error.
Yes, sir.
If it happens here,
Then
then
it
it
is
is
half
half
LSP.
LSB. If it happens here,
Yes, sir. Minus half LSP.
minus half LSB. That's what is offset error.
Yes.
Then what do you mean by gain error? It is the separation between the first
The first
transition to
transition.
last transition.
Last
You can say
transition.
last transition is happening here. This is your last transition.
Yes,
Last
sir.
transition to first transition. If the separation is VFSR minus 2 LSB, then I say there is no gain error.
Yes, sir.
Correct? So this is about the offset error and gain error. So let us consider a situation where you have the transitions are happening so shall I write a solid line joining the midpoint of the transitions? So I will write a
Yes, sir.
line.
Ideal.
Let me just write a transition line. Where is my okay? No, it is scale. I don't have a bigger scale. Okay, I'll just draw through this. It is passing to the midpoint of the transition. Okay, this is my assume that a typical this is fine. This is as per the ideal one. Whereas the
Yes,
second
sir.
one has slightly extended. See now, this is not stopping here. This is going another half LSB more. Correct?
Mm,
Next one
yes,
is
sir.
just half LSB. Just half LSB. But the next one is starting from here. It is going till 1 LSB up.
Yes, sir.
The meaning of this lengthy line is if the input voltage changes from here to here, it is represented as 001. The
Yes,
meaning
sir.
of this line is whether the input voltage is from 5 times 1 by 16 to, so this is 5, 7, 9. So this is 9 times 1 by 16. From 5 to 9 half LSD, output voltage is 011. 011. Next, assume that, okay, this is happening here, and this will go another half LSD mode, another half LSD mode. Then this is this, and this is this. Carefully observe this. I'm writing the ideal as well as a typical one.
Yes, sir.
If you notice, if the input voltage is, uh, just notice these bits. So this, and this. Can you see this 100 is not at all the output for this particular ADC?
Yes, sir. We're not getting that value.
You're not getting this. You're not getting this representation at the output at all. Meaning, if the
Yes, sir.
input voltage is 9 half LSB, it is this. If it is slightly more than that, you're getting it as what?
Next value. Yes, sir.
101.
101.
You are either getting 011 or 101. This is actually missing.
Yes, sir.
Why it is missing is because of this error in your representation, not in your representation, in your output sensitivity. Since your ADC is sensitive, it is giving the output voltage for all these voltages same bit. So you are actually getting what? You are getting a missing bit. Can you see there is a missing code or missing bit is happening?
Yes,
What is
sir.
the missing code now? You are not getting this code at all.
Yes, sir.
This code at all you're not getting. So now what we'll do, we will draw, as we draw a line passing through this centers. So actually what happens there is, okay, prior to this we have another half LSB that you can assume. This you can assume here, that's why this has become the midpoint. And what is the midpoint of this? What is the midpoint of this? Is it somewhere here?
Yes, sir.
Is this the midpoint of this code transition? Is this the mid? Is this
Yes,
is the
sir.
midpoint? Is this the midpoint? Is this the midpoint? So what I'll do, I will join the midpoints.
Yes, sir.
Of course, let me just show in the textbook how it is happening. This is what is you are having. You're exactly having a solid line which is passing through the ideal transitions, and this is a dotted line which is passing through the midpoint of this width, midpoint of that width. Maybe I'll just share this textbook with you people. So what is this dotted line? Dotted line is known as core center line.
Okay, yes,
Core
sir. Center line.
center line. Because this is certainly passing through the center of that particular core.
Yes, sir.
Center of this is midpoint. This is the midpoint of that. This is, of course, you are considering another half as there ideally over here. Can you see here? There is an error from, there is a separation from
That
this to
line.
this here, this to this.
Yes, sir.
This we call it
There is,
as,
sir.
this we call it as INL, integral
Okay. Yes, sir.
nonlinearity error. Can you see there is a INL existing from the ideal to the typical code?
Yes, sir. There is.
And if you can see this okay, ideal blue line, what was the code length? What was the code length here? Was the code length equal to 1
It was one
LSB?
LSP. Yes, sir.
Now,
It was.
see here, what is the code length?
It's two LSP.
Here. It is one and a half
One and a
LSB.
half, sir. It's
How much is this here?
okay. It's half
It
LSP.
is half LSB. Here, 2 LSB.
Two LSP.
Here it is one and a half LSB.
One LSP.
It is half
Half
LSB. Here
LSP.
it is 1 LSB.
One.
Of
Yes,
course,
sir.
I'm considering this. See now, what was the code length of ideal case?
It has to be one LSP everywhere.
Ideally, code length is
One
1
LSP.
LSB.
Yes, sir.
Typically, it may be other than 1 LSB. Other than 1 LSB. Suppose if the code length is 1 LSB, I will say DNL is 0.
Yes, sir.
This is DNL is equal to 0 if the code length is 1 LSB.
Yes, sir.
Now you can see code length is keep changing. It is now
Of course.
DNL is
Plus half LSP.
half LSB minus half
Minus half.
LSB. It is now
Plus one
1
LSP.
LSB plus 1 LSB, and this is what?
Minus one. Okay.
Plus
But
1.
so that one 100 we won't take
You
consideration,
are
right, sir?
not getting, why you are not getting is because one of the DNL is more than 1 LSB.
Yes, sir.
You will have a missing code if the DNL is more than 1 LSB
Yes,
or
sir.
equal to 1 LSB, because this is actually the representation of the next code that is being represented by the previous code itself.
Yes, sir.
Because of this error in your ADC, you are missing a code here.
Yes, sir.
Even though the number of bits are 3, where you're supposed to get 8 combinations, but you're getting only 7.
Yes, sir.
So what is the number of bits you are expecting? You are expecting number of bits as 3 having 8 combinations, including 000,
Yes, sir.
because 000 is a combination.
Yes, sir.
Including 0, if the number of bits are 3, I have to get 8 combinations. In the same 3 bit, I'm not getting 8 combinations. There is one less. One less. Why this one is less? Because my error is more. Correct?
Yes, sir. Okay.
Because
It
of
is exactly
more
2
error,
LSP.
because of more error. Now the error is not like this. The error is not
Yes, sir.
like
It
this.
will be
In
plus.
some cases, it shoots up. It shoots up. Can you see
Yes,
the
sir.
error is going up to plus 1 LSB and it is going up to minus 1 LSB?
Yes,
When
sir.
the error
In that
shoots
case.
up, then your signal to noise ratio will increase. Sorry, will
Yes,
reduce.
sir.
It will reduce because noise increases.
Yes, sir.
When signal to noise ratio reduces, then the number of bits is not 3 now. I will say it is
Yes,
not
sir.
3. Why it is not 3 means you are not getting all 8 combinations.
Yes, sir.
In such case, we will write one more important concept of effective number of bits. ENOB. Effective number of bits of an ADC. You say that n is equal to 3 bit, which should give 8 combinations. When you're getting only 7 combinations, then shall I say number of bits are still as 3? I can't say.
Yes. We cannot
Number
say.
of bits are less than 3, even though it is not practically true, because you cannot have number of bits other than 2 or 3.
Yes, sir.
Why we are saying it as effective number of bits is when the signal to noise ratio is less than what is expected. Okay, assume that okay, if n is equal to 3, what is the signal to noise
Yes,
ratio
sir.
here?
It was around 1920, sir.
Just give me exactly.
Yes, sir.
Okay.
6.02 into 3 plus 1.56. Sorry, the 19.82.
19.82 dB is the signal to noise ratio. Assume
Yes, sir.
that because of something like this error, this signal to noise ratio is reduced to 16 dB. This has
Yes,
reduced
sir.
to 16 dB. Why it has reduced to 16 dB? Because my noise is more.
Yes, sir.
So then we can actually find what is effective number of bits. So how do I find effective number of bits? Is I'll use the same equation. Shall I write it as 6.02 n plus 1.76 dB is equal to signal by noise plus some distortion?
Yes, sir.
This is signal to noise ratio. I'm just writing it as instead of writing it as signal to noise SNR, I'm writing it as signal divided by noise plus distortion, which
Yes,
is
sir.
same as SNR. Okay, this is same as SNR. So shall I write it as 6.02 n is equal to signal by noise to distortion minus 1.76.
Yes, sir.
Shall I say now n is equal to signal to noise ratio, of course, signal by noise to distortion ratio 1 minus 76 divided by 6.02.
Yes, sir.
Now let us consider if n would have been 3, what was the maximum signal to noise ratio? It would have been this. Assume that now
Yes, sir.
noise has increased. Let me say it as 16 minus 1.76 divided by 6.02. Can you give me what is the number here?
Yes, sir. 16 minus 1.76 divided by 6.02. So it's 2.36.
See now, this is the effective number of bits. Why this is the number of
Yes,
why this is the effective number of bits? This should have been actually 3 if this was 19.82.
82. Yes, sir.
Suppose you substitute 19.82 minus 1.76 by 6.02 and exactly
We'll get
becomes
3.
3. Meaning
Yes,
there
sir.
is no other distortion. You are getting the exact transitions happening at every odd number of half LSBs. So in such
Yes,
case,
sir.
n will become 3. Suppose if something like this happens, suppose if something like this happens where signal to noise ratio has reduced, will exactly end up with ENOB. What is this ENOB now? E stands for
Effective number of bits.
effective number of bits is your ENOB. So ENOB is given by signal by noise plus distortion ratio minus 1.76. This is actually in dBs. dBs divided by
Yes, sir.
6.0. This will actually give an idea. Suppose, let me just take up an example which is there in the textbook. So you consider there is a 10-bit ADC. There is a 10-bit ADC,
Yes, sir.
and VFSR is VFSR is. I'm just taking the same example. 10.24 volt. Signal to noise plus distortion ratio is 56 dB.
Yes, sir.
They are asking what is the effective number of bits. As the number of bits are 10 already, it's already given,
Yes, sir.
but they are asking what is the effective number of
Effective
bits.
number.
That
Yes,
means
sir.
to say, if there was no distortion, what would have been signal to noise ratio maximum as per this?
This will be 560.
This has been 6.02 into 10 plus 1.76, correct?
Yes, sir.
This would be 60.2 plus 1.76. This would have been 691. It would have been
Yes.
61.96 dBs.
96. Yes,
But
sir.
what is the signal to noise ratio now? You have 56
5060.
dB. So can you see the noise has increased?
Yes, sir.
So since
Yes,
the
sir.
signal to noise ratio has reduced, you will going to have
Noise
a
is.
reduced number of bits, effective number of
Yes,
bits.
sir.
So what is that ENOB for this particular example?
It will be 56 minus 1.76 divided by 60.2.
6.0.
Sir, 0.9.
It's not 60.2, it's 6.0.
Uh,
Is it 9.01?
yes, sir. Exactly. Sir.
So what do you actually mean by this now? What
It
is
has
2
been
power
reduced
10?
by 1 bit.
What do you mean by 2 power 10? What is 2 power 10? Is it
512.
1000, 1000,
1024.
1000 2 power?
24.
What is 2 power 10? Sorry, 2 power 9.
512, sir.
See now, if the effective number of bits are 9, even though you have 10 number of lines, 10 number of lines for this ADC,
Yes, sir.
you will not get 10,024 different combinations. You will not get it. Why? The noise is so high that you will get hardly 520 combinations,
512.
512 combinations, because it is 9.01, maybe slightly more than 512
Yes, sir.
combinations. Getting the point now? Meaning,
Yes, sir.
if the input voltage is 0 to VFSR, you would have ideally got 1024 different combinations.
Yes, sir.
Because of
Yes, sir.
more error, you will get only 512. Another 500 codes will be keep missing.
Oh, yes, sir.
Meaning, here you can see in the previous case, you're not getting 100 at all. You're not getting 100
Yes,
at
sir.
all. Likewise, for this 10-bit ADC, you may lose half of the representation because the
With
noise
this
is
error. Yes, sir.
with a
Too
signal
high.
to noise ratio of 56 dB. So the intention here is we should have ENOB close to value of n. That is possible only when you reduce the distortion. Only when you reduce the distortion.
Yes, sir.
How do you reduce the
SNR should
distortion?
be too
Uh, okay, if there are any questions, let us just answer them. Is this ENOB clear? So we had an example, of course. ENOB comes from this also. Here you can see. Uh, suppose if you say, what is 2 power 3? 2 power 3 is 8, no?
high. 8. Yes, sir.
2 power 3 is 8. 2 power x is 7. Then what is x? Suppose in this particular case, are you getting only 7 combinations?
Yes, sir.
So then 2 power x is 7 combinations. I'm looking at what is the effective number of bits. This x happens to be effective number of bits. What is x? 2 point. Hello.
Yes, sir. It is
You take that much time.
2.807.
2.807. So since the effective number of bits are so and so, you can actually find what is that signal by noise plus distortion. What is this error? So error will not be, sorry, signal to noise ratio. What is the ideal signal to noise ratio for this? This would have been 6.02 into n
Into 2.
plus 1
3,
point,
right?
sorry, sorry, into 3. Into 3,
3.
1.16. Correct?
19 points, sir.
Okay, we already found out 19 point. Where is that?
82.
19.8.
82, sir.
If it is 2.8, what will be signal to noise ratio? 6.02
6.02 into
into
2.8 plus
2.8,
1.7. So it's 18.616.
18.616 dBs. Can you see the error is more here? Sorry, the signal to noise ratio is less. Why
Yes, sir.
signal
It
to
is less.
noise ratio is less is the error is more here. Error is more. Suppose if you
Yes, sir.
actually ask to plot the EQ, shall we plot the EQ here for this one? Is
Yes,
it
sir.
something like this? Fine.
Yes,
For
sir.
this,
No issue with it.
will it go like this?
We'll
Will
go
it
much higher.
extend? This is fine here. This is fine. But here it goes down till 1 LSB.
Oh, okay. Yes, sir. There the extension happens.
Can you see here? And then
It
and
will
then where
only
it
go
goes,
up to the half, zero.
it will go up to.
Just half left.
So will it
Zero
actually
position.
come?
Up to there.
Is it up to here?
Yes, sir.
See here, this is here. You are representing. Will it go here?
Yes, sir.
Then
Top. Then again it will come full down. So I mean 1.5 LSP.
now here you can see. Now what will happen?
It's
So no,
shooting
no,
up, right?
no, no. Will it go till this point or will it just go till only here?
Only till zero, right, sir? Because
Zero here.
half LSP change. Yes, sir.
Then what happens? Here you can see.
Then it has to come down.
Will it come like this?
Yes, sir.
So
Only
now
half LSP will come down. Again, it will shoot into 1.5.
I'll just leave it to you people. Write the
Plot the
EQ
curve.
here. Just write
Yes,
the
sir.
EQ because you have this reference. You have this reference. Keep in mind at this point, ideally it should be 0 dB. Okay,
Yes, sir.
zero half LSD. So there should not be any error. If it is other than that, you may have to look into. You may have to look into that. Correct.
Yes, sir.
So let me just see okay, how you draw this. What is that? Quantization
Plot.
error. Quantization error is maximum over here,
Yes, sir.
and it is minimum here. It's minimum here and minimum here. You can see, sorry, here. It is minimum here, and it is the most here, and it is same. Of course, it will be same quantization here. It will be same quantization here and here, but it is the maximum quantization here for this DNL of 1 LSP. DNL of 1 LSP.
Yes, sir.
Okay, this is about the specifications of ADC, where we talked about offset error, the gain error, missing code, code center line, and then we also talked about what is that? Effective number of bits. Effective number of bits. So we will have effective number of bits because the signal to noise ratio is lesser than what is expected. What is expected? In such case, we're going to miss some of the bits. Those number of bits, how many number of bits you want to miss out? That will be a representation of something like this. So instead of what is exactly 2 to the power of 9.01? 2 power 9.01. What is the exact number? Okay, 2
515.56, sir.
515.56. Okay, you'll get 515 combinations instead of 1024. So you'll be
Yes,
worried,
sir.
okay, why I'm not getting some combinations? It's because your signal to noise ratio is very poor in that ADC. In that ADC. Okay. Okay, the next class we will just consider practical implementation of ADCs. Okay, one thing before we close, so I was just going through yesterday what your